Let us verify Rolle's theorem for the function fx equal to x times x minus 1 whole thing square in the interval 0, 1. Now if we want to verify Rolle's theorem, then we need to check three things. First one is f is continuous. F is continuous. But you see that f is a polynomial function. F is a, and we know that all the polynomial functions are continuous. So continuous, it is continuous throughout R. So in particular in the closed interval 0, 1. Again, f is a polynomial function. So second point, we need to show that f is differentiable. So if it is a polynomial, then it is also differentiable. F is differentiable. We don't need whole of the closed interval, we just need to show it on the open interval. So it is differentiable in the open interval. Last point that we need to make sure that value of the function at the end point are equal. F of 0, if you compute f of 0, simply 0 times anything is 0, and f of 1 equal to, if we compute 1, again 1 times 0 is 0, so f of 1 is also 0. So third point, we observe that f of 0 equal to f of 1. The value of the function at the end point, their end point are 0 and 1. The value of the function at the end point are same. So if these three conditions are satisfied, then the Rolle's theorem is applicable. Since all the three conditions are satisfied, the function is continuous in the closed interval, the function is differentiable in the open interval, value of the function at the end point are equal, Rolle's theorem is applicable. Now Rolle's theorem, if it is applicable, then the Rolle's theorem says that there exists a constant c, there exists a constant c such that f dash c equal to 0. Now what is f dash c? You see that fx is given to be a polynomial and we know how to differentiate fx. But fx equal to x times x minus 1 whole thing square. So it is product of two functions. Therefore f dash x, fx equal to x times x minus 1 whole thing square. So it is a product of two functions. Therefore f dash x equal to first function, that's simply x, into derivative of x minus 1 whole thing square. We are simply applying the formula uv rule, d dx of uv, that's simply equal to first function u times v dash plus v times u dash. First into derivative of second plus second into the first times derivative of second plus second times derivative of first. So first times derivative of second plus second times derivative of first. Derivative of x minus 1 whole thing square, we can apply power rule. So 2 times x minus 1, 2 minus 1 plus x minus 1 whole thing square times 1. Okay, we can simplify it. We can take x minus 1 common. When we do so, we will be left out with 2x plus x minus 1. That's equal to x minus 1 times 3x minus 1. Therefore, we have computed f dash x, or derivative of fx. So f dash of c equal to c minus 1 times 3c minus 1. So Rolle's theorem assures us that there exists a constant c such that f dash c equal to 0. There exists a constant c such that f dash c equal to 0. Now we have computed f dash c to be equal to c minus 1 times 3c minus 1. Now f dash c equal to 0 if c minus 1 times 3c minus 1 equal to 0. Now product of two number equal to 0, then one of them has to be equal to 0. So either c minus 1 has to be 0 or 3c minus 1 has to be 0. If c minus 1 equal to 0, then we can say that c equal to 1. If 3c minus 1 equal to 0, then we can say that c equal to 1/3. Now once again we need f dash c so that we need a constant c so that f dash c equal to 0. That is possible when c equal to 1 or c equal to 1/3. Now we want a constant c so that f dash c equal to 0 and that c lie in the open interval 0, 1. C has to be greater than 0, less than 1. What is that constant c? Does such a constant c exist? The answer is yes. 1/3, 1/3 is greater than 0, less than 1. So we have determined a constant c. So we found a constant c equal to 1/3 in the open interval 0, 1. A c lie 1/3 lie between 0 and 1 such that f dash c equal to 0. So we have verified Rolle's theorem for the given function fx equal to x times x minus 1 whole thing square in the interval 0, 1.